Very exciting. Well, we've been talking a lot about the A-Lab. We're also steps away from it. Would you be up for doing a quick tour?
Oh yeah, let's go.
Yeah, all right, let's make it happen. Awesome, well here we are in the A-Lab. David, thanks for having us. Show us around. What are we looking at?
All right, so here, this is the computer where everything starts. So you come here, for example, to go and set what is in the dosing head. So the materials you are going to use for your synthesis. Then in this computer, you can also go and set the experiment you're going to run. So everything starts here. So you submit your experimental data here. Then once the computer receives your experiment, it's going to do the stoichiometry reaction and see for the recipe how much you need of each material. Then we go to the powder dosing station, where this robot arm here takes from the bottles there, and from each bottle puts in the balance, doses everything inside one of the plastic containers that are in the background. I will show you very soon. So after everything is dosed, it goes to the ethanol dispensing station, that one, and dispenses the ethanol inside the container. Then puts the lid back on the container and brings to this central machine here, which is the speed mixer. So then everything is mixed. Then they come here to this station that does the removal of this liquid and place inside of the ceramic crucible. Then the materials are now in a liquid form, right? We need them to be dry. Then they would go to this drying station here that dries all the ethanol. And then from here they go to this circular structure. There's the one you use at home. I forgot the name.
Like a dolly, maybe?
Yeah.
Yeah.
So then this one here is the connection between you and the machine, or between the robots, right? So then from here, they come to this window where that robot arm would come and pick crucible by crucible and bring to the ceramic racks there, and they go inside the furnaces.
Wow.
So then we can do up to 8 samples at a time.
So these are the famous furnace doors?
Yes, these are the yes, they're the ones. So then they go inside the furnace. We can do reactions in air here, and we can do reactions that are not in air on these furnaces that are on the floor. They are tube furnaces. So we can control the environment, the atmosphere, for example, by using this for like argon, oxygen, or nitrogen. So then from here, after the reaction is performed, we have to take the sample and then do the analysis. So then now we go to the other side again to do the, to show you DASH, the powder recovery. So, and then here in this station is where we have, after they are baked, they would go back to the trays there. And then this robot arm here is going to take from the crucible, bring the crucible to the ball dispenser, which is right there, the tower. So as you can see, like a lot of 3D printed parts. So this lab here was designed, the powder station was designed by a company up from our request. But then this side here is like us, we made this part. And then we have here, for example, the crucible receives the ceramic ball from that tower, then goes to the shaker. The shaker right there is where the crucible is going to be, shaking this ball inside to grind this material. And then after it is totally ground, we dispense in one of the plastic containers. And then the plastic containers are going to be, they need to have their cap changed. So some caps, they have sieves, and that's how we dose the powder onto the disc. And the extra the disc, later is what goes to the XRD machine.
Those are the XRD disks right there on the
Yeah.
black panel?
Mm-hmm.
Okay. And that goes
And they
into
go
this.
here.
Okay.
Yes. And then from here the data is obtained, and then they go back to the computer and the cycle continues.
We've come full circle.
Yes.
This is incredible. Wow. Okay, so a couple questions for you. Let's back up. So we start off with this machine, as you said, moving into this unit here.
Yes.
One of the things I noticed is there's a big old Mitsubishi logo on this robot arm.
Yeah.
You mentioned that some of these, I guess, pieces of equipment you've manufactured or made, others are kind of purchased. I'm curious, like how easy or difficult do these different vendors make it for you to be able to put these materials or put these robots together, orchestrate them through this robot software that you talked about?
The vendors are amazing. We never had any issue. They actually do a great job on everything. So whenever we need support, they're always there. So I never had any. I mean, since I'm here, we never had any issue that I can recall on anything. And then Labman, for example, that made this for us, they understood the assignment. And as you can see, this look amazing. So of course we would like everything to look this way, but the lab is growing, right? So then we have many. For example, another example I can give is the tube furnace itself. So MTI made that tube furnaces for us. So we said we need something like this, and then they're like, okay, challenge accepted. Then later they got the tube furnaces for us. And I think, like I mentioned before, some companies are trying to manage this need that is, we need the equipment to work and do the job, but we need to go beyond that. I think the standard very soon will be on all the equipment having at least some automation level. Maybe the equipment is not automated to do the whole work, but could be just, for example, the robot arm doing something. So speed mixer, for example, didn't make this fully autonomous by standard, but in this situation here, this machine works with the whole software that Labman made to make this flow work well.
So it sounds like it's a really collaborative process with the vendors where you're giving them your requirements and they're saying challenge accepted.
Yes.
Are they actually coming into this space and looking around and looking at dimensions and
many times?
Yeah.
So people from Universal Robots came. I'm pretty sure they're from Universal Robots, but some people from the robotic arm vendors, they came to visit us, and in the university where we are expanding the A-Lab, there they are even providing training for us because we have this mobile robot. And we need to learn how to use it. So they came to, and they, the experience is always great. It's very nice. I think engineers go well together.
So then you've got these containers. What did you call the name of? Is it crucibles here?
Yeah, the crucible is the ceramic one.
Okay, the ceramic one's right there.
The plastic one is the vial one.
Okay. And then you have in those
the bottles.
The bottles. Those are the different. Is it powders that you have?
Yeah. So
Okay.
every single one of them are different materials. Sometimes we have, like, if we need a lot of one material, we can just have more of that material in more than one bottle. But I think that only happened once.
So there's also really an inventory thing that you are having to manage as well, which making sure that you have, as these computers maybe have different hypotheses for what they want to be creating, you need to make sure that there's ample supply of that.
Yes.
Okay. Is there, I guess, how much of this material do they go through in a typical run?
Oh, no, it's not a lot. So the A-Lab makes very small amounts, right? So you're working on like 1 gram, 1.5, 0.8 grams. So we usually make like a few amount of materials per run. So it's not, they last a good time.
Well, you mentioned the furnace doors. I want to again check out your
Yeah.
masterpiece here that you that you were
The very
developing.
initial one. Yeah,
Yeah.
we can come closer here.
Okay.
So the
Wow.
robot's paused, so it's safe to come.
Okay. Cool.
So yeah, it's very basic. It's just an aluminum structure. In this case, a sensor here for the door. There's already a sensor inside this linear actuator that turns it off automatically when retracting. And the reason why we stop in between with the sensor is because even though there's a sensor to stop it when it's fully extended, we are not fully extending. We have to stop in between. And then we have this safety pin here. And if someone needs to open this, they can just pull the pin and open the door immediately for any safety concerns. And yeah, and then we have this aluminum extruded structure to just go around. So it's a very cheap structure, you know, that then we have the controller there, the black boxes. That's each box control, 2 of them, and it's working since from the very beginning. So it never failed. So we are aiming, you know, now with the expansion of the lab to have more of the electronics being on PLCs, and this one is still on an Arduino. But for 3 years, you know, 2.5, let's say, everything is working really well.
What are PLCs and what's the advantage of moving to them?
So PLC is a programmable logic computer, and they are the industrial standard for these applications where you need to control machines, right? So they are very robust. Their time on acting upon sensors, you know, for example, not many, I'm pretty sure all of the safety that's regarding, like, for example, an elevator, you know, all of the sensors on the door to keep people protected are from PLCs. So it's and then we have different tiers. So here you're using only the very basic automation ones, but for some applications you need to have the safety level ones. So fire extinguisher systems, they also are based on PLCs as well. So many of these industrial applications, when they touch the automation side, the PLC is what brings that. So you can connect to this unit all the sensors and the actuators, and then you have this software that never basically breaks. It runs constantly, you know, thousands per time per second. They're analyzing the sensor, you know. So I think an Arduino can analyze a sensor 16,000 times per second is the time you can analyze a sensor or an input. You know, that's the time that the clock of the processor. And then the actions are based on this speed. This is why things are so fast. And then you can have the safety devices that their clock speed is way higher. So then we can trust that these machines are actually protecting our lives around these strong motors. Imagine the size of the motor to move an elevator, right? You don't want that motor not being controlled by something, you know, that is not very fast to know, you know, immediately that something is wrong.
Wow. I notice you have 4 furnaces here. Tell me about the need for 4, and how does that relate with, I guess my natural question is, are there multiple basically flows happening at the same time, where as something is baking, you can create another experiment and have a lot of parallel processing?
Yes, definitely. This is what happens. So I can have one batch coming in, and then the ALab OS even analyzes if, for example, let's say you have a reaction, and then some other scientist comes with a different reaction and sees that the temperature of the furnace will be the same for both of you, and the profile is the same. So then this software is going to try to combine your samples with the samples from the other scientist.
That is so smart.
It's really cool. So all these tasks happen at the same time. And the process, of course, are parallel. So I can have new samples being prepared while I'm recovering the powder here to prepare for the analysis, while other ones are being analyzed right now. So it keeps going. So we can have people constantly having new experiments being inserted, and the lab is going to manage everything, calling us from time to time just to clean some things.
That's amazing.
So, and the question about 4 furnaces, right? It's because we can only have 4. If we had more space, we'd have more than 4. That's for sure.
There we go. There we go. So, donors, I hope you're listening. Open up those checkbooks. Let's create a larger space here.
That's right.
And have more than 4. Amazing.
We want to expand the lab as maximum as possible.
Yeah.